Now in this quarter, we shall discuss alpha decay from theoretical point of view. In the scattering experiment of alpha particles are allowed to incident and come in close proximity of the scattering nucleus. The Coulombian repulsion between two increases when the nucleus and alpha particle are just touching each other. The repulsion is maximum. If the kinetic energy of alpha particles is larger than the Coulombian repulsion, then alpha particles will overcome the repulsion and will enter the nucleus. At this point, suddenly the alpha particle enters in the region of nuclear force where it is attracted by nucleons in the nucleus. This interaction between the nucleus and the alpha particles can be represented pictorially by the potential energy curve as shown in the diagram appearing on right side of your screen. The rising portion from A to B, which is appearing on the screen, I'll try to show you this portion from A to B. This indicates increasing electrostatic repulsion of alpha particles as it approaches the nucleus. The sharp fall from B to C, here you can observe from B to C, this is a step kind of potential, is essentially in the region within the nucleus, implies the attraction of alpha particles by the nucleons present in the nucleus. Calculations based on Coulomb's law show that the point B corresponds to the energy of about 25 mega electron volts for higher Z element. I mean to say that this potential is of the order of 25 mega electron volts. So here the scale is already mentioned. This is in megavolts. So fine. Hence, it may be concluded that alpha particles of energy less than 25 mega electron volts, which are coming from outside, I'm talking about the experiment of alpha scattering in which He24 is incident from outside. Now, He24 with energy less than this level 25, they are repelled if they approach to the nucleus from outside. So this is outside. If the potential barrier prevents the access of alpha particle from outside the nucleus, the same barrier should prevent emission of alpha particles from interior of the nucleus. I mean to say that if some particle wants to escape in a classical manner, then this particle should also have energy level of the order of 25 or even more than 25 mega electron volts. However, it is surprising that some radioactive elements emit alpha particles with low energy, that is 4 mega electron volts. So you can identify 4 mega electron volts energy level. This is something 5 and this will be 4 mega electron volts. For number of natural radioactive alpha energy particles. So from this physical situation, alpha particles with less energy of the order of 4 mega electron volts will not be able to escape the nucleus because it has to overcome the internal potential barrier which is appearing of the order of 25 mega electron volts. Classical mechanics has no explanation to alpha decay process. In 1928, Gurney and Condon of USA and Gamow of Russia independently developed a theory which is later known as Gamow's theory of alpha decay to tackle this problem of alpha decay using quantum mechanics. So here classical mechanics has no explanation for alpha decay process. So we are going into the shelter of quantum mechanics for this explanation. This theory is known as Gamow theory. According to classical mechanics, an alpha particle having energy 5 to 10 mega electron volts inside the nucleus cannot cross the potential barrier and escape if its energy is less than the maximum height of the Coulombian barrier, which is about 25 mega electron volt. But quantum mechanics predicts that there is a definite but small probability that such a particle from the interior can be found outside the nucleus. In other words, there can be a definite probability, rather there is a definite probability that alpha particle can escape from the nucleus even its energy is less than that of the top of the potential barrier. Thus, quantum mechanically there is a finite probability that alpha particle leaks through the potential barrier as if there are holes in potential barrier. This effect is called as quantum mechanical tunneling or simply tunneling. So for discussion of the Gamow theory, we are going into the realm of quantum mechanics, and it is expected that you are quite acquainted with at least Schrodinger's time independent equation. In order to explain the phenomenon of alpha decay, Gamow has made following assumptions. An alpha particle may exist as alpha particle within heavy nucleus, which we are considering getting leaked or finding a tunnel. Such an alpha particle is in constant motion and is held in the nucleus by potential barrier. The third one is there is a small but definite likelihood that alpha particle may tunnel through the barrier despite the height of the barrier each time it collides with the barrier. Based on these assumptions, Gamow derived the relation for the probability that alpha particle may tunnel through the potential barrier. In order to make these calculations simple, we shall consider only one-dimensional rectangular potential barrier of width L. So here this is width of the potential barrier is L and height of the potential barrier is V. So it is marked as V. Obviously, this height V is greater than the kinetic energy of alpha particle. So this arrow we shall refer to the advancement of alpha particle, and the energy level of this is a way smaller than the height of the potential barrier. This rectangular potential barrier as shown in the figure has three regions of concern. So this is the first region in which alpha particle is coming. This is the second region in which alpha particle is crossing the higher potential barrier, and the size of the barrier width is L. and then the further transmitted alpha particle is entering into the third region where we are detecting alpha decay. In region 1, incident and reflected alpha particles or waves associated with alpha particle are present. So here you can see a nice wave progressing towards the potential barrier. This incident and reflected wave we are going to consider mathematically. So here only advancing wave is being shown. Mathematically we shall consider incident and reflected both. In region 2, both forward moving transmitted waves and reflected waves from the other side of the barrier are present. And in the region 3, only one forward moving transmitted wave is present. So here in the region 3 we are talking about only forward moving transmitted wave is present. Now let us deal with this problem in a mathematical way. V of x, that is the potential is 0 in the region 1. So the potential level is 0 here. In the range where x rolls from 0 to capital L, so this is the dimension of the barrier, rather width of the barrier over which the potential V is present. So this V present is like this. And in the next region where x is greater than L, so for region 3, the potential is again 0. Now we are going to apply the quantum theory to this issue. We have potential barrier of about 25 mega electron volts and alpha particle with energy 4 to 8 mega electron volts is trying to overcome this barrier, which is classically not possible. So the dimension of the potential well is single dimension. This is the point x equal to 0. This is the point x equal to a. Sometime I was referring this as L, does not matter. A is the width of the potential barrier, and here we have three regions. Like region 1, we have for x less than 0. Then we have region x equal to 0 to x equal to a, and the third region we have x greater than L. Now for this situation we have to apply the general expression, one dimensional case Schrodinger's time independent equation, and it is d2 psi by dx square plus twice m upon h cross square e minus v operated on wave function psi. This is equal to 0. This being one dimensional, psi is depending on variable x that I am writing here. Now we want to apply this expression to alpha decay process. So the potential barrier is of definite thickness, and that's also going to change. I'm going to discuss with you how that is going to affect our discussion later on, but for making calculations as simple as possible, we are going with the square wave potential. Now here for region 1, we have potential energy 0, V is equal to 0. So this expression becomes d2 psi 1 by dx square plus twice me upon h cross square psi. This is equal to 0, and here I would like to substitute k1 as under root of 2me upon h cross square, so that here we can plug in k square, and that becomes a standard differential equation. Now in the second region we have energy of the particle E 4 to 8 mega electron volts, which is smaller than the barrier height. Now we already know that E minus V is negative. So what we'll do, we shall write that minus sign here, and it is V minus E. And this quantity we shall plug in as K2, which is equal to under root of 2m into V minus E upon H cross square, so that this quantity for replacement is K2 square. Now again, in the region 3, we have V equal to 0, and we are writing that differential equation for psi 3, but the pattern is same because like region 1. So del 2 psi by del x square for region 3 is equal to twice me upon h cross square psi 3 equal to 0. So we have similar kind of equation for region 1 and region 3, whereas we have a bit different kind of differential equation for middle region, that is second region. Now these are standard differential equations and that possess standard solution. Psi1 is equal to a into exponential of ik1 x plus b into exponential of minus ik1 x for all x less than 0. It means that the wave is oscillating here and it can be reflected back. So we are encompassing both forward and backward solution. Then for region 3, the solution is of similar kind, only the constant is different. That depends on boundary condition that we are going to discuss to evaluate that. C times exponential of ik1x. The negative part I am ignoring by putting that involved constant 0, because here I am going to talk about only forward motion of alpha particle. Then in the middle region, the situation is a bit different. Psi 2 is equal to, first I am writing negative part and then I am writing positive part. Does not matter, that is for just mathematical ease. F into e to the power minus k2x plus g into e to the power plus k2x. This is for the middle region. So we have two similar equations, and the middle region we have a different equation. So here we have this set of three equations, psi 1, psi 3 of similar kind and psi 2 a different kind. I have rewritten this expression, and now I am going to differentiate this equation with respect to x. I mean to say that psi 1 dash, or rather in general psi dash, is partial derivative with respect to x of psi. So I am differentiating this psi 1 and writing this as psi 1 dash. This is equal to a times ik1 into same exponential plus b times minus ik1 into same exponential. Similar story applies for region 3, ik1 times c into e to the power ik1x, and for psi 2 dash we have minus k2 times f, same exponential, plus k2 times g into same exponential. Now I want to explore this as continuity condition at x equal to 0. Now to match the wave equations at the boundary of region between 1 and 2. So this was the kind of potential that we have discussed, and the wave is arriving here and it is entering into this point. Now I want to make it very clear that at this point our equation should be continuous. For that, psi1 is equal to psi2 and its first derivative should also be same, so that psi1 dash equal to psi2 dash at x equal to 0 boundary condition. So we are at the boundary between region 1 and region 2. Now let us roll through these equations. So psi1 is this expression that I have written here, and psi2 is this expression I have written here. And now further I want to plug in x equal to 0. So this whole term will be 0, e to the 0 will be 1. Here again e to the 0 will be 1, e to the 0 will be 1, and e to the 0 will be 1. So a plus b is equal to f plus g. So here the main objective that we are having in our mind to evaluate at least 4 constants out of 5. So I want to evaluate A, B, F, G, and then I shall eliminate separately C, that you will see when the discussion goes up. Now the second condition I want to impose that psi1 dash is equal to psi2 dash at x equal to 0. So here I have already written psi1 dash that I am writing here, and psi2 dash I am writing here. In addition to this, I want to plug in x equal to 0. So e to the 0, e to the 0, 1. This e to the 0 will also be 1, and this e to the 0 will be 1. So on simplification, we'll be able to obtain ik, which is common in this part, times a minus b, and k2 we can take common, and we can write g minus f, or minus f plus g, does not matter. So we can simplify this expression for a minus b equal to minus k2 upon ik1 f minus g. So this we have simplified. And the another equation that we had as a plus b is equal to f plus g. Now these expressions we can further explore to rewrite a minus b equal to minus k2 upon I times k1 f minus g, that here we have already done. So here I have rewritten this so that we can further evaluate for a and b. So these are important equations. We shall be referring these two equations later on. Now we are going to develop the continuity condition at x equal to a. So in this diagram we have potential barrier. This is region 1, this is region 2, and this is region 3. So this is at point x equal to a, this was the point x equal to 0. So continuity we are developing at x equal to a. So psi2 is equal to psi3 at x equal to a, and psi2 dash is equal to psi3 dash at x equal to a. This is the boundary condition we have. Now same equations I am rewriting psi1, psi2, psi3 and their derivatives psi1 dash, psi2 dash, psi3 dash. So let us compare the first part, psi2 equal to psi3, and substitute x equal to a. So here at all these points, at this point x equal to a, and at this point x equal to a. Similarly, at this point x equal to a and x equal to a again. So psi2 equal to psi3 offers us f into e to the power k2a plus g into e to the power k2a, that is equal to c into e to the power K1A. Similarly, making psi 3 and psi 2, psi 3 dash equal to psi 2 dash. So earlier we have done this equality. So we get this equation, and we can rearrange this equation: minus f e to the power minus k2a plus g into e to the power k2a. This is equal to ik1 upon the common point k2 equal to c into e to the power I times k1a. Now adding these two equations together, we can find g, and similarly we can find f in terms of c. C we are not touching. We have four equations. Earlier we had two equations. Now we have another two equations. So four equations we are exploring to find four constants, and these four constants are in terms of the fifth constant, that is c. So g we can rewrite as c by 2. How we are doing that, I guess I need to explain that. We have f into e to the power minus k2a plus g into e to the power k2a, that is equal to c into e to the power I times k1a. And the second equation we have minus f e to the power minus k2a plus g into e to the power k2a. This is equal to ik1 upon k2 equal to c into e to the power I times k1a. Now we are adding these two highlighted equations. So this term and this term here, it is cancelled, and we are taking this term twice. So this 2 is adjusted here, and e to the power k2, we are writing here e to the power minus k2a, and rest of the part is same. What is that rest part? Rest part is c we are retaining e to the power I times k1, c into e to the power I times k1, and here we have common part. This 1 is from here, and I times k1 upon k2, it's from here. So this makes expression by adding last two equations for g. Now subtracting two equations. So I shall refresh this slide for second subtraction. So to proceed for subtraction, I am going directly to that equation, and here this is the first equation I am having, and this one is the second equation. Now I want to subtract these two equations. So this minus this quantity minus this quantity will be plus twice f. So this 2 is adjusted on right hand side here. Then e to the power I times, sorry, e to the power k2a, sorry, e to the power minus k2a, e to the power minus k2a, here it is e to the power plus k2a on another side. Then this quantity minus this quantity same, it is 0. So g is eliminated here. Now c is common in both the case. E to the power I times k1, e to the power I times k1, this is common. So c e to the power I times k1. The remaining multiplier here was 1 appearing here, and the another multiplier was I times k1 upon k2 is appearing here. So this is how we have evaluated f and g. Now we shall substitute f and g in the expressions for a and b that we have already developed in the previous slide. Now we are going to refer f and g for substitution. A plus b we have already written it is equal to f plus g, and here we have g and f to be substituted directly here appearing in this equation. You can pause the video and verify. Then here you can take c e to the power I times k1 common. You can take 2 inside the bracket. We have e to the power plus ka e to the power minus k2a divided by 2, so that we can lead to hyperbolic functions. Then this term I k1 upon k2 is common, and e to the power k2a minus e to the power minus k2a upon 2 is common. This is just segregation of terms, and the first term leads to cos of k2a. Now here I want to tell you e to the power I theta. We write as cos theta plus I times sin theta. And if this is with minus sign, then if it is with minus sign, so this will be replaced by minus sign. Similarly, e to the theta is written as cosine hyperbolic cos theta plus sinh theta, sin h theta. And if it is, so this is for plus, and if it is minus, then for minus you can introduce here a minus sign. So you can add these two terms together for twice cos, and that 2 cos can be coefficient can be plugged here. So this is cos of k2a, and this is sinh of k2a, and the factor with sinh is I upon k1 upon k2 with a minus sign. Similarly, we can raise a minus b equal to minus k2 upon I times k1 f minus g. Again, I have to substitute f here and g from this point. By substituting that and simplifying and collecting terms together so that we can use hyperbolic cosine and sine functions, we can write a minus b is equal to c e to the power I times k1a cos of k2a minus k2 upon I times k1 sinh of k2a. Here we can take a proper collection such that the negative sign is absorbed, and we can write this as c into e to the power I times k1a into cos of k2a and plus I times k2 upon k1 sinh of a. So here I want to highlight that we have minus 1 upon I in the first equation. Then we are multiplying here numerator and denominator by I. So this I square will be minus 1, and minus multiplied by this will lead to simply I. So the substitution is minus 1 upon I is equal to I. So this substitution we are doing here. So this is the important equation which I have highlighted with red pen, that a plus b equal to f plus g simplified, and a minus b equal to so and so appearing on your screen. You can pause the video and verify the expressions. So collectively writing together a plus b and a minus b, we can rewrite a plus b, a minus b, and we can add this so that in addition this minus b plus b will be cancelled, and we are left with twice a c into e to the power I times k1a. Inside bracket we have 2 times this term, and I is a common quantity here in both the cases because I is in numerator, and sinh of K2A is a common quantity, and inside bracket we are left with K2 upon K1 minus K1 upon K2. Now we can rearrange this expression for A equal to C times. So we are taking 2 in the denominator of right hand side, and here this 2 and this 2 will be cancelled. However, here in this term 2 will appear in the denominator, which reflects here. So cos of K2A plus I by 2, K2 upon K1 minus K1 upon K2 times sinh of K2A. Similarly, we can subtract two expressions so that A is eliminated and twice B is equal to this term. So when we are subtracting this, this minus this, so A minus A will be 0 and B minus minus B will be twice B. And here this term and this term is cancelled and we are left with only imaginary part, C times I times C times e to the power I k1a into this imaginary number I times inside bracket we have minus k2 upon k1 minus k1 upon k2 times sinh of k2a. So B, we can reorganize this expression for B, so dividing the whole expression by 2, so 2 is reflecting here, and minus sign we have taken out as common here, and now I am interested in A upon C because transmission coefficient I am going to write in this term. Transmission coefficient expression I am going to write A into conjugate of A divided by C into conjugate of C. So here you can look at this expression for mod A square upon mod B square, mod C square, sorry. So this type of transmission coefficient I want to write, and to make it I need A upon C. So I have rearranged this expression for A by C. Similarly, B by C, I am not going to use this. For your convenience, I am rewriting A by C, B by C, and the transmission coefficient C star, that is C into C conjugate divided by A into A conjugate. So this expression for transmission coefficient looks like on your screen. So this can be further simplified by collecting identical terms, that is K2 upon K1 minus K1 upon K2. There is a kind of similar term we have collected together, and cos square K2A plus 1 by 4 times, so I square will be minus 1, and so minus this, rather I should say I into minus I will be 1 that way, and this 2 into 2 will be 4, and same bracket into sinh square K2A. Now we have identity cos square x minus sin square x is equal to 1, so I can write cos square x is equal to 1 plus sin square x. So for this I am going to write sinh square K2A plus 1. Let us do that. So this offers us this equation. Now we shall proceed further. Now I am rewriting the last expression, and here we have sinh square K2A, sinh square K2A common, and inside bracket we have 1 plus 1 by 4 times this, and this leads to this kind of expression. Now K2 and K1 we have to substitute. K1 square is twice me upon h cross square, and K2 square is twice m into bracket v minus e h cross square, and K1 square plus K2 square is twice mv, where v is potential, upon h cross square, and K1 square into K2 will look like this. So here what we are doing, we are expanding this by substitution, and we'll be able to make a concise form of the expression in terms of energy potential as T is equal to 1 upon 1 plus 1 by 4 V square upon E into V minus E sin square K2A. Now this I want to write same quantity to the power 1. Instead of 1 by x, I am writing x to the power minus 1, and now I am rewriting this expression for t equal to 1 plus 1 by 4 v square upon e into v minus e sin square k2a to the power minus 1. Now I am writing some expression as sin square x equal to 1 by 4 e to the power 2x plus e to the power minus 2x minus 2. So this identity I am exploring, and instead of x I am interested in k2a. So here this expression is 1 by 4 e to the power minus e to the power 2 times k2a plus e to the power minus 2 times k2a minus 2. Now note that K2A is very large as compared to A. So e to the power K2A will be further large than unity. So I can ignore this same quantity 1 upon, that will be very small, and 2 also is a very small number to be ignored. So it is 1 by 4 e to the power k2a. We are almost done with this mathematical treatment, and I am writing sinh square k2a as 1 by 4 e to the power k2a in the same expression. And now this 1 by 4 into 1 by 4 will be 1 by 16 in later term, and as I said that this quantity is very large, so I can ignore this quantity and rewrite that expression, and it will be 16e v minus e divided by v square e to the power minus 2k2a. So what I have done, I have taken again reciprocal of this so that the power will unity again. So 16e into v minus e upon v square e to the power minus k2a. Now I am just ignoring all smaller quantities. I am considering this as unity that does not matter, and transmission coefficient is e to the power minus 2k2a. We already know what k2 is, and a is width of the potential well, and transmission coefficient we have unfolded. So this is the transmission coefficient for fraction of alpha particles undergoing penetration. And if we take log to the base e on both sides, log to the e of transmission coefficient is equal to minus 2 k2a. Now we are carrying forward the previous equation, t equal to e to the power minus 2k2a, that is log to the base e of t is equal to minus twice k2a, where the meaning of k2 is under root 2m upon h cross square inside bracket v minus e. Now if we suppose that at any moment only one alpha particle exists inside the nucleus according to the presumptions of Gamow theory, and that moves back and forth along the nuclear diameter twice r0, then the collision frequency nu we can write velocity upon distance, and velocity I am representing by v, while the distance is diameter, that is twice r0. Typically The value of velocity of alpha particles is found 2 into 10 power 7 meter per second. This can be calculated from the energy 8 mega electron volts, and R0 is of the order of 10 to the power minus 14. Let us plug in these values and we get answer 10 to the power 21 attempts per second. Now, our transmission probability represents that alpha particle knocks at its confining wall 10 to the power 21 times in a second, and yet it may wait for an average time as much as 10 to the power 10 years to escape from the nucleus. So our transmission probability, I'm using the same equation which I have encapsulated here, and alpha particle inside the nucleus faces the barrier of varying height and width. Here you can see that the height of the returning potential is changing while the thickness of the well is also changing. So here we are considering uh, log to the base e as ln t equal to minus 2 integration 0 to capital A, 0 to small a, k2r dr, where we are rolling our potential over the width and it is changing, it is not constant, and the variable introduced is r in place of thickness, integration k2 function of r dr over the width. Now we have to work out this integration k2r dr over the limits r0 to r, where r0 is the radius of the nucleus and r is the distance from the center at which v is equal to e. Now here you can see that this is the level of energy 8 mega electron volts, and for this we are considering this r as distance from the center at which v is equal to e. The variable r equal to capital R is at potential energy equal to kinetic energy. It means that kinetic energy is the kinetic energy of alpha particle and potential well is this we have shown in the diagram. Now this is a recap equation, and the last equation was ln to the base t equal to minus 2 into integration k2r dr, limits rolling from r0 to r. Now the potential of alpha particle twice E is the charge on alpha particle and Ze is the charge on daughter nucleus. So the electric potential of these two entities will be V equal to twice Ze square upon 4 pi epsilon 0 r, where small r is the distance between two, and here we are substituting this value of V. So under root of twice m upon h cross square we have picked up from here. Then V is being replaced by the electric potential twice Ze square upon 4 pi epsilon 0 r, and at that point we are talking about small r equal to capital R is the place where potential energy V is equal to the kinetic energy of alpha particle. So here we are making some adjustment r upon r, where r is equal to r, and we are replacing this quantity by electric potential V, and that V is equal to E. So we want to take E common, and here we have adjusted E here, and we are left with the bracket under root capital R upon small r under root of minus 1. So our equation becomes ln t is equal to minus 2 under root of twice me upon h cross square, and we are left over to solve this integration. In the next slide, we shall solve this integration. Now let us rewrite the back equations, and we want to solve this integration. To solve this, we are going to substitute small r is equal to capital R into cos square theta, and dr will be minus 2r sin theta into cos theta d theta. So we shall substitute small r equal to capital R into cos square theta. So this r is cancelled here, and we are left with 1 upon cos square theta, and this 1 upon cos square theta minus 1 can be further simplified by trigonometric identities, and this dr is being replaced by minus 2 r into sin theta into cos theta d theta. So here this 1 upon cos square theta minus 1. So minus 1 I am writing as cos square theta upon cos square theta. Now denominator is cos square theta, and 1 minus cos square theta is sin square theta divided by cos square theta, and actually this quantity is under root of, so this will be under root of, so we are left with sin theta upon cos theta. So sin theta upon cos theta is to be replaced by this bracket sin theta upon cos theta, and cos theta will be cancelled. We'll be left with minus 2r into sin square theta d theta. Now sin square theta is 1 minus 2 cos theta upon 2, and the integration of this will be so this 2 I can cancel here, and here we are left with integration d theta will be simply theta, and integration cos 2 theta is sin 2 theta upon 2. Now from this substitution, this very substitution, cos square theta is equal to r upon capital R, and cos theta is equal to under root of r upon capital R. Sin theta is under root of 1 minus cos square theta, so under root of 1 minus r upon capital R, and sin 2 theta is equal to 2 sin theta into cos theta. So I want to plug in this value here, so 2 will be cancelled in the next line, and we'll be left with sin theta into cos theta. So cos theta is this, and sin theta is this. So we are left with minus r cos inverse of under root of r upon r. Here we want theta, and cos theta is equal to under root of r upon capital R. So theta is equal to cos inverse of under root r upon r minus under root r upon r into under root of 1 minus r upon r. So we shall rewrite this expression on the next slide. So the basic equation with we have started is this one, and we have solved this integration, and we have obtained this is equal to this much, and by substituting we have minus 2r into under root of twice me upon h cross square into inside bracket cos inverse of r upon capital R in the under root minus under root of r upon capital R into under root of 1 minus r upon r. So I'm rewriting these equations, and here we have identity cos of pi by 2 minus theta is equal to sine theta, and sine of under root r0 upon r is approximately equal to under root of r0 upon r. And when we are performing cos of pi by 2 minus under root of r0 upon r, this will be simply equal to under root of r0 upon r. So taking cos inverse on both sides, we are left with pi by 2 minus under root of r0 upon r is approximately equal to cos inverse of under root of r0 upon r. Now ln of t we are substituting back in this last equation, that is equal to minus 2r under root of twice me upon h cross square. And what we are doing, we are writing cos inverse of this under root r0 upon r as pi by 2 minus under root of r0 upon r. So here we have substituted this minus under root of r0 upon r into under root of 1 minus r0 upon r, and under root of 1 minus r0 upon r is approximately equal to 1. So we can further simplify this as 2 times under root of r0 upon r. Now we are going to make final substitutions. So here E is equal to this, E is equal to potential V, which is we have already discussed, twice Z E square upon 4 pi epsilon 0 capital R, and this can be rearranged in terms of R as twice Z E square upon 4 pi epsilon 0 E. So we have interchanged the role of E and R, and we can substitute back the value of R here, which is actually 1 upon R. So it will be 4 pi epsilon 0 E upon twice Z E square. The rest of the equation remains the same. Now this can be further simplified as 4E upon h cross under root Z R0 m upon pi epsilon 0 minus E square upon h cross epsilon 0 under root m by 2 Z into E. Here Z is the atomic number of daughter nucleus. Substituting all constants, we can obtain ln t is equal to 2.97 into under root of ZR0 minus 3.95 Z under root E. Now all energies can be substituted in form of mega electron volts, Z being the atomic number of daughter nucleus. We can rewrite that log t to the base 10. We are shifting from log to the base e to log to the base 10, and the constants are changed by the multiplying factor, and this equation appears like this. So this is the final equation we have, and this one is after substituting the numerical values. Now we have again previous equations. Lambda is equal to nu times capital T, and we have seen that nu is equal to V upon the diameter, that is twice R0, and taking log to the base 10 on both sides, we obtained log of lambda to the base 10 is equal to log of V upon twice R0 to the base 10 plus log of T to the base 10. Now we can substitute this value here, and we obtain this equation. Now the experimental data, now we can compare here. Here you can see on x-axis we are plotting z into e to the power minus 1 by 2. So this is x, then this is the slope m with a minus sign, and log of lambda to the base 10 we are plotting on y-axis. So this is equal to y equal to mx plus c. Slope is negative. Now as I said here, this being your x and this quantity being y, this slope is minus 1.72 and this quantity is c. Now this fits very well. You can see all the data points around a line, and the least square fit of the line offers 1.72 slope, 1.72 slope, which is exactly matching as per the Gamow theory. The radius of the nucleus R0 can be determined from the position of the line is just about what is obtained from nuclear scattering experiment. The theory predicts that the decay constant and hence the half-life should vary strongly with alpha particle energy E. This is indeed the case. The slower decay is that of thorium-90-232, whose half-life is 1.3 into 10 power 10 years, and the alpha particle energy is 4.05 mega electron volts. And the fastest decay is that of polonium 84212, whose half-life is 3 into 10 power 7 seconds, and the energy of those alpha particles is 8.95. So these experimental data points, they are best fitted in the line, and the best fitted line equation has slope 1.72 and the involved constant pertaining to the radius of the nucleus that exactly match with the experimental things. So this is the grand success of the Gamow theory, and Gamow was awarded Nobel Prize for this work along with his two contemporaries from America. So here we can substitute values of K1 and K2 that we have started with into this equation for transmission coefficient, and this transmission coefficient is appearing in this fashion. If we substitute gamma is equal to under root of 2mv minus e upon h cross square, we can write transmission coefficient as e to the power, that is exponential of minus 2l gamma. This represents a real quantity, that is a definite probability of finding a particle in the third region. So that is what we are calling tunneling, and this contradicts the classical picture. It depends on the mass, barrier thickness and energy difference V minus E. So here you can observe, I want to highlight also this transmission coefficient. It depends on barrier width, barrier thickness, size of the nucleus, you can say. Then the energy difference V minus E and mass of the particle which is crossing the tunnel. So finite but exponentially decreasing probability of penetration exists. This is a revolutionary thing. When classically we think that, for example, we have such a mountain and then we have a car. A car is rolling from this point. So when the car is rolling from this point, the free fall will allow you to go maximum. If you reduce the frictions, it can go up to this level. It will never cross the barrier, and will exit here. However, quantum tunneling suggests that it can find a path for alpha particle to escape through this barrier. So here we can substitute values of K1 and K2 that we have started with into this equation for transmission coefficient, and this transmission coefficient is appearing in this fashion. If we substitute gamma is equal to under root of 2mv minus e upon h cross square, we can write transmission coefficient as e to the power, that is exponential of minus 2l gamma. This represents a real quantity, that is a definite probability of finding a particle in the third region. So that is what we are calling tunneling, and this contradicts the classical picture. It depends on the mass, barrier thickness and energy difference V minus E. So here you can observe, I want to highlight also this transmission coefficient. It depends on barrier width, barrier thickness, size of the nucleus, you can say. Then the energy difference V minus E and mass of the particle which is crossing the tunnel. So finite but exponentially decreasing probability of penetration exists. This is a revolutionary thing. When classically we think that, for example, we have such a mountain and then we have a car. A car is rolling from this point. So when the car is rolling from this point, the free fall will allow you to go maximum. If you reduce the frictions, it can go up to this level. It will never cross the barrier and will exit here. However, quantum tunneling suggests that it can find a path for alpha particle to escape through this barrier. This is an interesting picture I want to show you. This is the wall of the nucleus, which we are considering in the form of potential barrier, and this is interior of the nucleus, and alpha particle with smaller energy is coming outside. This is the situation. So here you can relate, this is alpha radioactive nucleus. This has a potential barrier that we can chart like this, and alpha particle is having energy level of this order and the barrier is of this order. So alpha particle is escaping through the barrier. That is the picture. This is one more picture I want to show you, where I am showing you psi1, psi2, psi3, that is the wave function in 3 regions, and americium 241 is undergoing a decay with ejection of alpha particle, and the continuity from region 1 to region 2 offers a smooth changeover of a wave function at this point, and across the boundary psi2 to psi3 again we have a continuity. This continuity consideration has given smoothness to the wave function, and we could evolve the involved constants. Now here we have probability expressed as 10 to the power 21 times the transmission coefficient, and this is the transmission coefficient in our format. Now m, that is mass of alpha particle, is we can consider 4 times mass of proton. The energy E is equal to 4.2 mega electron volt. This is the energy with which alpha particle is emitted. The potential barrier that it is crossing, 30 mega electron volts, which classically we feel impossible, but with quantum tunneling we are calculating things, and the barrier width we are considering 2 into 10 power minus 12 meters. So this offers us probability 10 to the power minus 18 per second, or we can write the average time, that is equal to 10 to the power 11 years. We are now exploring Waterloo Maple software for analyzing the mathematical equations just now we have derived. Maple 2020 version is loaded and the active output screen is in front of you. That represents the graphical response of the program developed in Maple for quantum tunneling of alpha particles. We shall set the rectangular potential barrier in the region 2 with a width, say small a, and we can vary the size of the potential barrier width. So here the first variable that I have is this one. I can vary the width of the potential barrier. At the same time, I can vary the potential of region 1, but I am not interested in making it other than 0. Similar is the case for potential of region 3, say V3, that also I am setting to level 0. Now the potential barrier V2, that is for region 2, I can raise the height of this potential barrier as desired. The energy of alpha particle is less than V2 here. So we shall set it to some lower value than V2. Now I shall enable the real function psi, real part of the function psi. So here you can see that the wave is coming, getting incident at this point and then going further but with diminished value. Now I am reducing the width of the potential barrier. As the width of the potential barrier is sizably small, then you can see the transmitted wave going through the region 2, which is shrinked into the region number 3. As the size of the or the width of the potential barrier reduces, the amplitude of the real part of the wave reaching into region 3, we can call transmitted into region 3, is increasing. Now we can have a look at imaginary part of the wave. The wave function psi, imaginary part with green shade, you can see on your screen, and the complete wave function psi is appearing on your screen now, and if you like to see the probability density, it can also be seen. Now the whole story depends upon the width of the potential barrier. So as we go on changing that, we can see the effect. Here I am rolling the screen forward so that you can see the transmission coefficient T present in this case and the reflection coefficient. And if you like to see the animation rolling over time, you can have a look at this for a moment. So as the time rolls, the wave is advancing towards the barrier, crossing the barrier and penetrating through. So with increased transmission, with smaller size of the width of the potential barrier, you can have a look. Now if we reduce the barrier height, then the transmission probability increases and smaller energy alpha particles can transmit through the potential barrier when the barrier is much higher than the energy of the incident particle. Thank you very much.